also have a ship. You can monitor the ocean, the different type of the ocean water parameters. And the India is the valley cubed, and we have all the ships, aeroplanes, satellite, and we monitor the land, ocean, the atmosphere. You can see the satellites, and the satellite, the ISRO's satellite, NASA satellites, European satellites, Japanese satellites, and each and every poor country, they have also dream of launching satellites to monitor their own countries. You can see how much satellites we have and what is the advantage of these satellites that we get the if something happens, we get information within 30 minutes or half an hour or 1 hour. And then the satellites say, if you collaborate with the international agencies, you get the information number of times on hourly basis or daily basis. And you might have seen in the news, we have space platforms, and now there are 5 astronauts in the space. They are monitoring the whole thing, Earth, and they are doing a lot of experiments. And then you can see here, the satellite has a lot of potential. It monitored the lights over the globe. You can see April 5th, 2020, how the light looks like, and you can compare in the past, 2016, and then you can say that this government has really did a lot of things. It has provided the electricity in the Indian villages, rural areas. Okay, so the satellite can also gives you, provide you information about this. And the credit goes to Abdul Kalam. He's the no more. And also the Dr. Vikram Sarabhai, late Sarabhai, and they had uh, established the Indian Space Research Organization, and now we are reaching to the Mars, and we are planning to reach on Moon. Okay. So I told you that we try to monitor the uh, the, uh, the growth of the babies. And you can also see how I was looking earlier when I was young with a black beard, and next to me is my wife. And then you can see here my beard started uh, changing the color, and now you can see what completely this guy was in Rajasthan, and all these information we get from the photographs, and now you can see here. And then I want to show you this picture, maybe 20 years back, and with the Shah Rukh Khan. And here is the latest picture. Okay, so the photographs, it gives you a lot of information about the growth and about the aging. Okay, and you can see the changes. This is my village, and you can see my my 1960s. This the whole uh, our house in the village, and now it has the partitioned, You can see next to this, another tree house has come up. So these are the changes. And the changes we monitor taking photographs. And the photographs provide evidence about the changes. Taking photograph is also known as remote sensing. And the, so earlier in 1962, the NASA took very high resolution photographs around the globe. The resolution was about 5 centimeters, and those images are known as corona image. And this corona image was, nobody knew this, but when Bill Clinton visited India, then it became disclassified, and now you can buy corona image of 1962, 64. You can compare the changes of any place in India and all.
Ayush,
Okay, now you can see here satellite has become very powerful, and the young people, you can note down this web
Sorry,
link.
sir, for interruption. Please, can you share your screen? We cannot see anything on the screen.
No,
Everything is visible. Just pin on the sir presentation.
or
Everything is visible.
everything is visible.
Sir, please continue, sir.
Okay, so what is the problem? People they say, do you see this? Do you see this?
Yes, yes.
Okay,
Yes, sir. Yes, sir. Everyone visible.
Yes, sir.
okay. So you can see this link. Young people, I invite you that note down the web link, and you can see the image of every day. And I took image of 19th June, and I know what is going to happen in Delhi. Delhi monsoon is going to come, okay, in a day or two, and now this area is occupied by the cloud, dense cloud. It must be raining. Okay, so Delhi, you can wait for some time. So this web link can provide you the daily images. And you know, I wanted to become a pilot, but then I became a teacher. So you can see the small plane. Uh, I was flying with a small plane in BHU, 60 hours, and then we were doing in Germany, and the Germany while we were doing this, we were monitoring the lake in Berlin. Okay, so you can see the pilot. We are sitting there in the back. There are the sensors, instruments. We were taking compact airborne spectrographic imager. Okay, so let me tell you, remote sensing, as I told you, taking photographs with a camera is also known as remote sensing. And in the remote sensing, we use the electromagnetic spectrum. When the remote sensing started, it started with the one wavelength, two wavelength, and now we have a hyperspectral. Hyperspectral means so many wavelengths. And when so many wavelengths, let me explain to you what is the advantage of so many wavelengths. The advantage is, suppose if I'm giving talk for 45 minutes now, you will not know about me. But if I start giving a talk from morning to evening, okay, then you get a lot of information. Same thing, we are using a hyperspectral remote sensing now. We can get information about any object in detail. Earlier, when the remote sensing uh, was not there, people were using pigeon. So, what is the basic principle of a remote sensing? The remote sensing, you can see the sun rays incident on the earth, and then it is reflected back. It is recorded by the satellite, and we try to analyze this data. And from the data, we get an image, and then we use this image for different applications. And you can see so many satellites orbiting. And these are well-known satellites, and we try to use these satellites for different applications. So you can see the satellites. There are so many satellites: MODIS, MISER, AVHRR, so many satellites. What is the information we get? We get information about the aerosols. What is the aerosols? Aerosols are suspended tiny, tiny particles in the atmosphere. Then you get information about the clouds, water vapor, greenhouse gases, and then we calculate the radiative forcing. We get information about the fog, haze, and smoke. During winter time, Noida also suffer with the fog. During also Diwali festival, you suffer with the fog, haze, and smoke. So you get information from the satellite data. And once you get it, you can take different type of information, and you can see different layer information you get, and then you can visualize using the geographical information system, which is known as GIS. GIS has become also very powerful tool to visualize the dynamic Earth. You might be knowing about the Google Earth. If you see the Google Earth map, then you will see the different cities, and you can overlay information about the road, about the borders, so you can visualize and you can calculate the distance from one point to another point. So that is based on the GIS, that is the Geographical Information System. So you can see here, you get information about the street map, you get information about the population, land cover, land, and then you can visualize this, what is happening around you. So this is the remote sensing. In the remote sensing, you use a shorter wavelength. The shorter wavelength, and you see electromagnetic spectrum is the broad wavelength. Broad wavelength means longer wavelength, shorter wavelength. In the satellite remote sensing, we use this shorter wavelength. Why is the shorter wavelength? Because the shorter wavelength has a very high intensity. You might be knowing, some of you, about the Planck's law, which is known as Q is equal to hc over lambda. The intensity depends on the shorter wavelength. Please turn off your mobile phone, otherwise we all get a disturbance. So we use a shorter wavelength. The shorter wavelength, the another reason is the shorter wavelength requires a shorter antennas. The longer wavelength requires longer antennas. But the satellite is a very small body, and longer antenna you cannot use in the satellite. And this is why we use a shorter wavelength. And the longer wavelength is used for getting information about the deeper inside the earth. I'm a geophysicist. I was going up to 200 kilometers below the earth. And if you ask me what is located in Delhi, what is located beneath Himalaya, what is located in the central part of India, I will be able to tell you because I used longer wavelength earlier. So you can see here from the longer wavelength, you can map the fault lines, you can map the lineaments, and you can see here is the Gangotri. Ganga comes from here, the Yamuna comes from here. This is Yamunotri. And so the satellite data provides the detailed information. If you go here or there, you may not visualize the fault line, but the satellite, you can easily map the fault lines. So this is since Sushil asked me to tell about some basic thing, everybody should learn what is the Maxwell's wave equation. These are the Maxwell's four equations. When you see the Maxwell's wave four equations, then you can see this equation. Uh, this is J omega epsilon E is the sigma E is the conduction current. This is a displacement current. And in the high frequency, we use the shorter wavelength and a high frequency. In the high frequency, we use the dielectric properties. The electron wave propagation depends on the dielectric properties of the media. So the dielectric properties is very, very important. So what I, and let me also tell you the basic thing, if you want to understand about the frequency. This is the frequency X band, C band, L band. And L band is about 23 centimeter, C band is 6 centimeter, X band is about 3 centimeter. And X band, C band, L band, you can see if the L band is higher here, 23 centimeter, the signal can penetrate through the tree. In the X band, the wavelength is only 3 centimeter. The signal cannot penetrate. So if it cannot penetrate, you cannot get information within the Earth. So in the satellite, we use the shorter wavelength. When it is shorter wavelength, we get information up to few centimeters. So after this, after my talk, Prashant is going to tell you. Prashant, he uses microwave remote sensing, and he might be telling you more about the soil moisture and the other information. The basic idea comes from the dielectric properties. And the dielectric properties, if you are if you have studied physics, you might be knowing about the complex dielectric constant in the higher frequencies. This is the real part, this is imaginary part. And you can see how the real and imaginary part varies. And they are very sensitive to the soil moisture. The first paper I wrote when some of you are not born in 1984, related with the remote sensing. And this is the dielectric properties and the microwave remote sensing. How the dielectric properties is important in the microwave remote sensing. And anybody wants to use this, you write to me or you can download this paper from Advances in Space Research. And then this is the basic paper to know how the microwave remote sensing controls is related with the dielectric properties. And then after that, I worked on the dielectric properties in Canada, and we studied about the dielectric properties of the clay and the sand, and also the effect of the salinity. This has a lot of advantage in remote sensing. At the same time, it has also advantage in the oil exploration. And you can see that we measured a lot of dielectric properties. Uh, and also, you can see with the frequency, how do the ISRO decides about which frequency we use? This is all depends on the dielectric properties. And depending upon what is our objective, what do you want to do, what are the applications for we are trying to use the satellite remote sensing. And this is for that, we have to measure the dielectric properties. And you can see here, we try to measure the spectral reflectance in the visible remote sensing. And all the reflectance, the dielectric properties help scientists to decide about the frequency of the sensors of the sensors which we put on board in the satellite. And you can see how we did it. And in Kanpur, IIT Kanpur, we made a stand to keep the radiometer here and then measured the reflectance of the vegetations, reflectance of the roads. And you can see here the reflectance of the vegetation. And this reflectance at 700 nanometer, because the vegetation contains the chlorophyll concentration, as a result, the reflectance becomes very high. And all these help us to develop the tool to measure, to map the vegetation, and which is known as a normalized difference vegetation index. And you can see here, now satellites measure the multi-sensor data of land cover, ocean, and also we get information about different heights. I think I'm taking a lot of time. Sorry about that. Okay, and then we are using satellite data for different kind of natural hazards. These are the different kind of natural hazards. I'm not going to go through all these things, but you can see this. And this is about the flood that they, some of the places flood is we see the flood and how we can monitor this. We can monitor from the using optical remote sensing and also the microwave remote sensing. And this is, we use the microwave remote sensing to use the soil wetness index parameter, and Then on this basis, we can see when the soil wetness index parameters increase, then we can predict about the flooding area. And then let me also tell you about the every year we face a problem with the cyclone in the Bay of Bengal, in the Arabian Ocean. And this is the Hudhud cyclone. And uh, this work is done by Achans Chauhan. He must be listening um, this one, and he published this paper um, in 2018. Our collaborator with the Dr. Rajesh Kumar and Prasanjit, and we did the lot of things related with the cyclone. When the cyclone hits, how the total column ozone changes, and how aerosol's optical depth changes. And then I'm going to run this one about the Gujarat earthquake. You can see what happens in an earthquake, where the satellites provide the information. And you can see what we did in 2001. It is going to be 20 years very soon. And we did a lot of measurements on the ground and also using satellites. And you can see from the satellite pre-image and post-image, and we try to find out the chlorophyll concentration. But we found that after the um, earthquake, no, prior to the earthquake, chlorophyll concentration also enhanced in the ocean. Not only the chlorophyll concentration, the water vapor also enhanced in the atmosphere, and a surface temperature also increased. Okay, and then in an earthquake, we found the uh, oozing of the gases. You can see here in Bachau area where the earthquake a few days back, earthquake hit, and it's in the 2001 the earthquake. You can see the volcano type of structure. The water came as a fountain, and as a result, you can see from the microwave the brightness temperature response changes, and when the brightness temperature uh, gave beautiful characteristic of the microwave remote sensing. And this we found the enhancement of the carbon monoxide in the in the earthquake. And if you have question, why is that? You send me an email, and I'll be happy to answer you because I'm running short of time. Then I'm going to talk about the pollution problem in the Indo-Gangetic Plain. You can see here there was a French satellite, and what we found, the the air pollution in the Indo-Gangetic Plain. This was the first time we observed from the polar satellites. And as a result, I started pushing NASA, and then NASA gave us a Aeronet station. We deployed at IIT Kanpur. And I'm happy to tell you that since 2001, and now we have the Aeronet data from Kanpur. So atmospheric pollution, why it is important? Because it affects the climate. And what are the causes for the atmospheric pollution? And these are the causes. I'm not going to discuss this. And now, whatever effect we see on the ground, and now the aeroplane network has increased in India, and we are polluting the atmosphere. And you see every time during winter time, especially when the jet is flying, you get the contrails. And the contrails, what you observed, they're very narrow, and after sometimes it is widened. It means it is polluting the atmosphere. The adverse impact of the pollution is the health, weather conditions, monsoon. It affects the snow glaciers. It affects the visibility, ocean ecology, agricultural productivity, and it also gives you the acid rain. You can see over whole globe, the India, China is highly polluted. Apart from that, the other parts is also highly polluted. And the pollution, uh, India, China is the highly polluted over the years. But some parts in the world is polluted during winter time, during summertime. India, why it is polluted? And because of the coal-based power plants. You can see how the coal-based power plants has increased in India. So these are the coal-based power plants. In the Indo-Gangetic Basin, the power plants is the number of power plants is so many. You can see here the density of the coal-based power plants, and if you have gone to Singrauli, you can see there are 8 power plants in Singrauli. And then you go from the west to east, you see the brick lanes and chimney might be, you might be seeing this, and they are also sources for the pollution. And the remote sensing, you can use remote sensing for drought monitoring. Okay, I'm not going into detail, but this is based on the NDVI, Normalized Difference Vegetation Index. And this is what we try to monitor this, the NDVI. And based on the NDVI, we can see where the drought is going to occur. And then you can see the dust system. And the June, you might have encountered some dust in the Noida because the dust season is going on. And you can see over India, what are the sources of the dust? The sources is coming from the Arabia Peninsula, and also the Thar Desert also contributes to the dust. Can we monitor this? Yes, you can monitor this. These are the satellite image. Okay. And I gave you a link, and now onwards, if you're curious enough, you can observe this dust through the satellites. And that dust, sometimes it reaches in the Himalaya. When it reaches Himalaya, it affects the snow glaciers. And affect means the snow glaciers is going to melt. When it melts, the water discharge in the Ganga Yamuna River is going to enhance. You can see here one of the problems for the pollution is the crop residue burning in Punjab. You can see it, same satellite image. We saw this on a Modi's image, 30th October 2012. You can see how the plume, it starts from Punjab, it goes all the way from up to Bangladesh, and also it goes on the other side, Pakistan. And when it comes here, Delhi gets polluted. And polluted means you can see dense haze, fog, smoke there. The crop residue burning a threat to South Asian air quality. And if you monitor this total column ozone, and you you can see the enhancement due to the crop residue burning. And earlier we thought that it affects only the Indo-Gangetic plain. Now with the latest our paper and what we are saying that not only it affects the Indo-Gangetic plain, it also affects the central part of India. It also goes in the southern part of India, depending upon the wind directions and the wind speed. Okay, so in the 2018 we published this one, and it's then also due to the crop residue burning, we do not realize about the health implications because it emits the methane. And if you are interested, you can read this paper and easily available. And then now I'm very happy that Delhi, you are using the green firecrackers during the Diwali festival. It also contributes to the air quality, air pollution. Okay. So over the years, what we are doing, the we are suffering with the coronavirus, and and you do not know how much coronavirus we spread in the atmosphere since a long time. And what this is the corona image, what you see, the red one. But here I want to show you the corona in the atmosphere. And what you see, the circle one, these are the diesel. The diesel, if you see, the particle is small, tiny, tiny particles in the SEM. The diesel looks like this. On the diesel, especially in the dust period, a lot of dust is coming, and there is a coating on the diesel. You can see the coat, and same thing here happens in the corona. So as a result, the radiative budget is going to change. The atmospheric chemistry is changed in the atmosphere. We never realized this. And now, since the whole world is suffering with the corona, we know what corona is doing, but you can think of our atmosphere. The atmosphere has polluted, is polluted. Who is responsible? All of us are responsible. The Delhi atmospheric pollution and air quality, and the causes are the populations of vehicles, energy demand, and a crop burning in October and November. Can we do something? Okay, can we minimize this? Outcome of odd and even planned. Your Delhi chief minister, he tried his level best. He implemented odd and even running of vehicles, but no use. Why no use? Because the pollutants which is coming from the Punjab can only spread in the Indo-Gangetic plain. It cannot go in the northern side because of the towering Himalaya. So that is the big problem. How to improve this? Can we minimize atmospheric pollution in Delhi and improve air quality? Yes, we can do that. Okay. Tell your chief minister. And how? Do not tell your CM. Okay, Kejriwal, not your CM, Delhi CM. And if you lock down Delhi, then pollution is going to decline. And this is what we saw in the month of March. Prime Minister Modi, he he put Janta curfew, and then later on the complete lockdown. And in some states, the lockdown is going on, some cities, but the March, April, there was a lockdown. As a result, the impact of the lockdown you see over the whole globe. In Delhi, 60% air quality is improved. Seoul, 54%. Wuhan, 44%. And you can see Delhi, South Korea, Wuhan, uh, things have changed. Air quality is improved. And this slide I'm borrowing from Dr. Chauhan from Indian Remote Sensing. His paper has come up, and he saw that the water quality in Haridwar has changed based on the remote sensing. So he analyzed the remote sensing data, he and his group, and now this paper is published. Okay. And you can see the impact of Amphan, the cyclone. This is, you can see the before Amphan, how the data looks like green, and after Amphan, you can see from the NDVI difference vegetation index how things have changed. You see, and this satellite, you can monitor this one. So what I want that the Gautam Buddha University, you can deploy a purple air sensor. The purple air sensor comes in a $200. There are purple air sensors in India, and the purple air sensor can measure the PM 2.5. And there is a need you can deploy, and you can ask your VC to give you $200. You can monitor this PM 2.5. Okay, so here you can see this, what we published. Decline in PM 2.5 concentration over major cities around the world during COVID-19, and a chance who is listening, and the Biznor, he published this one, and then we did for India, and now I'm going to be complete this. You can see PM 2.5, how it has declined. And this, we took data from PM 2.5 at a different location in India. And this data we have taken from American embassies. Yes.
Sir, now you can summarize within 5 minutes?
Yes. So this, you can see this. This NO2 has also changed because the vehicles, there was a complete lockdown. There was no traffic, only the power plants. So NO2 has declined. So the conclusion, remote sensing has emerged as a powerful tool. Now we cannot live without satellite. I will encourage young students to start working related to remote sensing, hardware, software, algorithms developments, decision-making tools, and we cannot live without satellite. And there is NASA, ESA, or any space agencies or ISROs, they need people like you. And also, I encourage you to learn GIS tools so that one can integrate satellite data and visualize changes on the Earth, atmospheres, snow, and glaciers. And we are suffering with the earthquake. And the Delhi tremors, there were 11 tremors. And what I advise, and this came to Times of India yesterday, India needs to expand its seismic network to record smaller earthquakes occurring in the central and southern Indian shield as well. So this we need. In NCR, we have enough seismic network, and because if the earthquakes are there, Noida is also going to be affected. And also, I advise all of you to use mask, which is very important to save your life. Okay, whenever you go out, whenever you meet other person, you please use mask. Okay, I at the end I would like to uh, thanks my collaborator. He is a chance. He is a Biswajit Nath from Bangladesh. He is mm, Mishra, Ritvik Mishra. He is the only ninth grade student. Okay, in California, he is trying to do a lot of use the satellite data from different cities. He is my undergraduate student who published recently a paper from Valeria Villa, and then he is she is Shukla from the Dibrugarh University, and here is Ajay who is helping me. He works here at the National Seismological Center in Delhi, and he is a Dr. Prasenjit Das. He is working with Innova, and he is the Dr. Rajesh Kumar. He collaborates with the Chauhan and with us. He was the earlier Sharda University. Now he has joined the um, Central University Ajmer. Thanks to all my collaborators. Thank you very much. Thanks for listening. I'm sorry if you did not see my slides. Okay, and I will send a PDF file to Sushil. He can share with you. Okay.
Thank you
So
very much, sir.
thank you
Thank you so
very much.
much for a very detailed, interesting talk. In this talk, we have listened basics of remote sensing, various applications, beautiful pictures, and very nicely, sir explained about the detailed connection of the Maxwell equations and dielectric properties. And sir finally said about the atmospheric pollutions, not only in India and abroad, and particularly in Delhi. And sir also conclude about the corona infections to the atmosphere. Even he talk about the what is the changes in atmosphere chemistry in the atmosphere. Thank you very much, sir, for detailed this interesting talk. And I must say that I mean it is it's very we all are very fortunate to listen you, and I hope all the participants have got very good knowledge about remote sensing and its use. So now we can understand the importance of satellite, GIS, satellite data, even for our survival. So now I let us thank to sir, and now I am requesting to Dr. Bhanumati Panda to continue the session.
Thank you, sir, for giving me this opportunity to co-chair the session. I, Dr. Bhanumati Panda, take this opportunity to introduce our esteemed speaker, Dr. Prashant Kumar Srivastav. Dr. Prashant is an assistant professor at IEST, Banaras Hindu University, India. He was associated with Hydrological Sciences NASA, Goddard Space Flight Center as visiting scientist on SMMP satellite soil moisture retrieval algorithm development, instrumentation, and simulation for various applications. He holds the PhD from Department of Civil Engineering, University of Bristol, UK. His research focuses on the use of optical and microwave satellite synergy with weather research and forecasting for hydrological applications. Was the recipients of several awards such as NASA Fellowship USA, University of Maryland Fellowship USA, Commonwealth Fellowship UK. To his credit, he made 130 plus publications in peer-reviewed journal and published 7 books with reputed publishing houses. He is acting as associate editor in a number of journals of hydrology, Journal of Hydrological Sciences, Journal of Earth Sciences. Now, I would request Dr. Prashant to take over the session. Sir, please.
Hello, can you hear me?
Yes, sir.
Okay, good morning, everybody. Hello?
Yes, we are hearing.
Good morning, sir.
Good morning. Can you see my slides?
Are your slide?
No, sir.
Okay, wait.
I believe I have to turn off, right?
Yes,
Then,
yes, sir.
If this the turn on.
Can you see now?
Yes, Prashant.
Yes,
Now you make it full screen.
okay, it's full screen now. Can you see it?
Yes.
Okay. Thank you, Professor R.P. Singh sir, for a very nice presentation.
Thank you.
Hello? Professor R.P. Singh sir covered the basics of remote sensing in a very nice way, and he also demonstrated visual interpretation and remote sensing. He also gave various applications possible using remote sensing satellite. So this is just some advanced level of his basics presentation, that how we can retrieve precipitation using microwave data sets. And in this, I'm covering only precipitation, not soil moisture this time, because I can see the title. This is like atmospheric processes, so I think this is good to present precipitation retrieval in the instead of soil moisture. So what I'm going to present here is microwave precipitation retrieval using a variety of data sets. But before starting this, I like to introduce a little bit of what is AI and what is machine learning and how we can use this in different sciences. For example, here I'm using for precipitation. We can use it for any other thing also, like many people are using it for soil moisture. They are also using it for water quality. They are using also for other marketing purposes. There are a number of applications possible through this AI and ML. So if you go with the basic definition of AI and ML, so it is generally, if you go with the artificial intelligence or machine learning, it is demonstrated by machines, for example, by our computer or any supercomputing facility or high performance systems. In comparison to our natural intelligence, which is displayed by human and animals, like we have also some intelligence, and now we are demonstrating those intelligence using AI techniques, because those are more faster than us, and it can give values or record at a faster time interval as compared to us. So if you go for the AI textbook, like any AI textbook, they are saying this artificial intelligence by the word intelligent agents. So what is this intelligent agents? Intelligent agents are any device that perceive its environment and takes action that maximize its chance of successfully achieving its goals. And it's like any device or any algorithm that you are using for converting any signals or any thing from atmosphere or from environment into some demonstratable things. Like in my case, it is precipitation. Or in, you can also say that AI, what is AI? It is described by machines that mimic cognitive function. Cognitive function like our learning, problem solving, sensing, anything that human can do, we can say as cognitive function, and it can be demonstrated by artificial intelligence techniques. So there are a number of definitions available in the web, but what we are going to use here in this case, that how we can use AI to convert a radar or microwave signal to some useful output. For example, in our case is precipitation. So here, if you go with the precipitation, many people know that there are various form of precipitation exist, like rain, snow, sleet, hail. And if you go, most common is rain, because you know it is a falling drop of liquid water. other one is snow, falls when the temperature in a cloud is below freezing. Then sleet, rain that freezes at it falls, and then hail forms when a drop of rain freezes and strong wind carry them higher into a cloud. And there are some other forms also available like snowflakes and other things. So, but these four are very common type of precipitation. And we are generally in India, we are generally having rain in most of the part except for Himalayan and Northeast region. We have snow. Otherwise, we have most of the in India we have rain. And why this precipitation retrieval is important? Why we want to estimate precipitation in a more accurate way? Because precipitation we can use it for rainfall runoff modeling. We know what is rainfall runoff modeling because whatever rainfall is coming to the ground or catchment, it is converted to runoff if it is more than the other ground water balance equations. It's like evapotranspiration, groundwater flow, and other things. So we can this rainfall or runoff model is very important because if we have a rainfall proper estimated rainfall, then we can easily predict the discharge in rivers. Then we can also quantify other events like what is the deficiency in the soil moisture. We can also quantify other effective rainfall parameters. And we need this precipitation also in irrigation scheduling and demand. What is irrigation scheduling and demand? Because why we need irrigation scheduling? And irrigation scheduling is just like a when to irrigate and how much to irrigate. Means farmer need to know uh, when there will be a rainfall or when there will be a irrigation is needed and what is the quantity of irrigation that we need to put in the field. So if we have the accurate precipitation data, then we can model this irrigation things in a very accurate way. And then we have other uses of this precipitation like in weather and climate studies. Like we know how this precipitation is important. Like in India, monsoon is very important. So monsoon is due to precipitation. So if you know the exact amount or we can quantify precipitation in accurate way, then we can go for this weather and climate studies in a more accurate way. And then we have several applications like flood and drought that already told this possible using rainfall runoff modeling. And then it is also impacting our monsoon and other things. So how we can measure rainfall on a ground? So most common instrument that you can see on your on any building roof, like most of the weather station, they have this instrument we call as tipping bucket rain gauge. So it is if you see the tipping bucket rain gauge, it measures the rainfall with a least count of 1 millimeter and gives out one electrical pulse for every millimeter of rainfall. So it is if you see the diameter is around 30 millimeter. There is a receiver, there is a funnel, and there is a tipping bucket, and there is a storage tank, and there is a measuring tube. So whenever the rainfall happen, it goes through this funnel, and then when it is around 1 millimeter, then this rollers roll, and then you can have that reading in your device. So this is the most common rain gauge instrument that we are using for rainfall measurement. So why we need this ground-based measurement of rainfall? Because these are the most accurate measurement, and whenever we are developing any algorithm or any technique, we need to justify with the help of ground-based measurement. If it is giving a close agreement with the ground-based measurement, then your algorithm and your product is good. Otherwise, you need to look into your algorithm to refine it further. So, but what is the drawback of these in situ instruments? What is the drawback of this? Because this is the point-based measurement. So, and if but we need rainfall on a large spatial scale because this this rain gauge doesn't show us the spatial variability. And rainfall is like is because it is cloud. We need to quantify on a spatial basis, not on a point basis. So we need some other methods so that we can retrieve rainfall on a larger scale, and for that we are using microwave measurement. So if you see the microwave measurement for precipitation, so there are basically two type of things are there. One is from earth observation, means there are satellites outside earth orbit, and second is on the earth that we call as radar. That, for example, in this case is weather radar or Doppler radar. So many people see this type of antenna. And if you see that antenna transmit a signal at some frequency, then it hit clouds and then it return back, and during this there is a change in frequency, and then we use this change in frequency to model the intensity and the rain rate of the particular event. And it can be easily done using some suitable algorithm that we will discuss in next few slides. And other one is the Earth observation, and this is the most popular one. We call it GPM constellation, and this is Global Precipitation Measurement Mission. It is launched by with the help of several agencies by US like JAXA, and then the French agency, then European, then ISRO, then Defense of US, and then NOAA. So all these combinedly effort to give this GPM satellite, which is very high resolution and accurate for soil moisture, precipitation retrieval, and it provides the next generation must precipitation estimate by combining all the other satellite measurement. So you can see it is a very advanced mission, and it provides rainfall with the help of several other satellites. So there is a big satellite that we call as GPM Core Observatory, and it is like a very massive satellite, and there are several small satellites sending signals to them, and then it uh, collocate all the signals and give you a high resolution rainfall over the Earth's surface. So we can do rainfall retrieval or precipitation retrieval by using both the method, either using by ground-based radar or by using Earth observation satellite. Um, I hope you can hear me.
Yes, yes, yes.
Okay. Because the pin drop silence, that's why. So in recent decade, there are several AI and ML techniques emerged and as a powerful tool because it provides a more better result. It give you a fall at a faster rate, and we don't need to do always do human interference in the retrieval of precipitation. So these techniques, this ML technique is popular because of efficient learning, reasoning, and self-correction. We don't have to do every time correction, all those things to retrieve rain rate or any other thing of your interest. As I told in the previous slide that there are now there are very good satellite available. They are very sophisticated, and they are providing data at every 5-minute and 15-minute interval for precipitation things. So we have EIML technique developed. We have advanced satellite with us. So if we merge both of them, then we can have a very good precipitation retrieval at a global scale or at a regional scale, depend on our need. So in this, we can see that there are several techniques available, and we published a number of papers on this AIML technique in this radar or precipitation retrieval as well as soil moisture and other thing. So I'm giving some example thing how we are doing this. So for example, that we are going to use a cloud detection and estimation algorithm, and we published in this algorithm with the help of our NOAA and UK partnership. And you can see what is the main benefit of this algorithm. That is it's a automatic cloud detection and estimation algorithm. So if we can detect cloud in a proper way, we can detect what is the type of cloud, we can detect what is the thickness of cloud and other thing, then we can easily have some idea about how we can have this rainfall in a rainfall retrieval in an accurate way. So in this cloud detection and estimation algorithm, we use passive microwave images. I hope you know what is active and passive, because this active and passive is very common term in remote sensing. And passive is like dependent on sunlight, and active is have their own energy source. So this passive microwave imager, we coupled it with this is a TRMM tropical rainfall measuring mission, and we use their passive microwave imager and coupled with multi-layer perceptron, which is a artificial neural network method. Like our body, whenever we touch any object, what happens? We have neurons in our body. So neuron collect signal from the hot plate and send to your brain, and then brain access the signal, say that no, it's hot. And after that, you have to take decision that whether you should remove our hand or not, depend on the heating that surface. Same way, this multi-layer perceptron also work in the artificial neural network principle. In this, what we are doing, we are sending several passive microwave signal And then this signal, with the help of this, we train this algorithm that if this amount of signal is coming, or if it is more than the threshold, then it will there is a precipitation. If it is less than that, then there will be no precipitation. So it's a simple rule that we use in this multi-layer perceptron. And for knowing that whether there is a cloud exists or not, for that we are using naive Bayesian classifier, and it is for detection purpose. So by using naive Bayesian classifier, we detect the clouds, and then when we couple with the ANN or this multi-layer perceptron MLP model, we can estimate. So it is a coupling of our TMI, this is passive microwave imager from TRMM, and then we have classification algorithm that is naive based classifier, and then it go into the multi-layer perceptron, and then after giving some training, like we need to train our model first, like our brain. If you don't know what is the meaning of hot and cold, then it is not possible to take a decision. Same way, we need to train our model here also. In this case, we have some ground data set that in that we have our rainfall measured from the any rain gauges or any other devices. There are several devices available, like automatic weather stations. They have also this tipping bucket and other type of rain gauge measurement instrument. And then we have TMI brightness temperature, and like from microwave satellite. So we try to build a relation between the microwave brightness temperature or microwave other readings like phase and like polarization, other thing. And once we have developed something that if this amount of precipitation is there, then this relation exists. If there is no precipitation, then this relation exists. So model know that whenever there is a brightness temperature of this value, then there is a chance of precipitation. If there is less than that, there is no precipitation. So once we have provided some training data to our model understand when to take a decision. So here we do the this naive-based classification, that what is whether there is a cloud exists or not in the signal in the satellite image, and then we have this training based multi-layer perceptron, and then it give you some value. Similarly, we have other microwave imager also, like sounder. Sounder means it take reading by in a vertical way. Like we have SMAS, and then we have ECMWF, is a European Weather Integrated Forecast System, and we use these data sets also to train the algorithm, because they are providing a large spatial coverage. So they have proper quality control data sets, and by using this data set, we try to again train our model, and then we get some information that if there is this much of cloud liquid information is there, then there is a chance of precipitation. So once we have this algorithm ready, we tested with several data sets, then we applied on both ocean and land surface types. And we are using here two types of radiometric information. First is like if you go with the TRMM specific, we will see that there are humidity channels over there. There are other window channels from 19 to 90 gigahertz. So we use all these radiometric information like brightness temperature at these frequencies, and then we feed into our clouded model, and then we predict this rainfall. So here we use, like I told in the previous slide, which is developed for two group of input measurement. First, we use the brightness temperature measurement at a humidity profiler of 9 to 11, and then we use window from 12 to 18 channels, and then we trained algorithm according on different channels to get to get the performance, because performance testing is very important here. If your model is not performing well on the known location, you cannot use it for the unknown. We have to train our model, then we have to test on some known data sets, and then go for the operational applications. So here because ocean, if you see ocean physics and land physics, both are very different. Ocean is much calmer than the land, and we have lot of heterogeneity. So if you see the most of the algorithm performance, they are performing much better on ocean as compared to land. So for this, we need to train models separately for both ocean and land, and then we can see that this much information is available on the ocean, on the land. And accuracy is also different. Generally, it is seen that ocean accuracy is much better as compared to land. That I told, because of heterogeneity, we have all sort of things on the land, like we have buildings, we have plants, we have a river, we have lakes. But in ocean, we have only water, and it's only topography and other thing that impact those things. So this network is trained with this ANN backpropagation algorithm. Here we use the Leeuwenberg algorithm to train our MLP, multiple layer perceptron. And after training the algorithm, we, of course, that I saw that we need to do the validation. If there is a good validation, then we can release, otherwise not. We have to retrain our model with the different data sets. So you can see that after implementing this algorithm, we can see that we have obtained mean absolute error of around 0.004 millimeter, CWAP 0.09 millimeter, which is quite satisfactory as compared to other algorithm available in the technical literatures. So here it is performing better, but there is always algorithm are now coming up, so there is always a possibility to improve your algorithm by using several other techniques like bias corrections and other things. So you can do the bias correction of your brightness temperature, then you can implement in your algorithm. Then, excuse me.